right, these are the Unit 6, Day 13 notes. They start on page 35 of your packet. And this is kind of a catch-all. It's just kind of a day to work on selecting different techniques for anti-differentiation. We're still working with that same essential question, how do I incorporate what I know about derivatives to find antiderivatives. And today we're going to do some applications with graphing calculator. So that you can handle some calculator problems and be a little more efficient about doing that. Just a word about graphing calculator use on AP with AP level problems. And when they give you a graphing calculator, when they expect you to use it, and they expect you to use the functionality, so they will intentionally give you functions that are impossible to do by hand. When you look at these expressions, they're just impossible. There's no way you could do a derivative or an antiderivative by hand. So they really want you to use your math function capabilities on your calculator. So keep that in mind as you're working with a calculator. Okay, so you have a math 8 key for derivatives, and there's a math 9 key for integration. And so I just want to show you a couple of different ways to use that math 9 key, because you can use it in a couple different environments. Okay, so just take a second and maybe off to the side of your notes, sketch what this means. So the definite integral from 2 to 7 of 2x dx, right? Okay, so I'll pause the video and go ahead and sketch what that means. Okay, so if you're starting the video up, I'm assuming you have a sketch in front of you of what that, you should be able to have a visual picture of what that means. And it should look something like this, right? We know 2x is we typically had 2t dt there, right? When we were back sketching things and accumulating things underneath the function, or between the function and the horizontal axis. So this definite integral says, let's take a linear function, 2x, let's graph it, let's shade in from 2 to 7, and that region between the function and the x-axis will be the value of this definite integral. So it's a trapezoid. We can use geometry to find the answer, but we're going to use our calculator and kind of talk about the capabilities within the context of using this function, and then apply it for more complicated functions. Okay, so let's apply the fundamental theorem of calculus, part 1. That's the evaluation part. Go ahead and do the antiderivative here, right? It's x squared, right? Bump up the power, divide by the new power, so it's 2x squared divided by 2. The 2's cancel. And we're going to evaluate that from 2 to 7. Okay, so fundamental theorem of calculus says plug in the upper bound into the antiderivative, and then subtract, plugging in the lower bound, right? So sketch what this means. So take a second here to sketch what this means. And we've done these sketches in our notes before. Okay, if you started up the video, you should have a sketch kind of next to the other sketch, and it should look something like this, right? We know x squared is quadratic. We know when we plug in the 7 and the 2, we're getting function values, right? Because we know that the fundamental theorem, we know that accumulating a region between a function and the x-axis results in a change in a value. So we know that this is 7 squared minus 2 squared. 2 squared is 4. 7 squared is 49. So we should have a difference of 45. So that's the change in the value. Okay. So, if we make sure you get that visual picture. The table is probably not so important. But I just brought that back because we have done this in our notes from the previous day. Okay, so we're going to go through then using the math 9 for calculating, and just kind of make sure we're getting this value, because we want to be sure it's working properly, right? Okay, so let's take a look at this. So if we just did a math 9, so we're going to do a math option 9, fn int is function integration. So math 9, we're going to put in a 2 for the lower bound, arrow up, we're going to put in a 7 for the upper bound, we're going to put in our 2x and our dx. There we go. And so right from that calculation screen, we get a value of 45. So that works pretty nicely. The nice thing is that, and that's kind of option one, right? That's the first way to use Math 9. The second way to use Math 9 is you can actually use it for integration. You can actually use it to get the this graph. It takes a while though. Okay, I'm on option 2 here. This takes a while, and I'm working off of a TI 84 plus CE. It's the color one. It's the real sleek plug-in to charge one, and it does a pretty decent job at handling Math 9 inside the grapher. If you have a liquid crystal display, this will take forever. I don't really advise you to do it. Okay, but I'm going to do it here on my CE. Okay, so I'm going to go into my grapher, and I'm going to do a Math 9. So I'm going to integrate right inside my graph, my graphing capabilities. So now this is the interesting thing. I want to graph, and I want to graph the whole function x squared. So I'm going to start at 0, and I'm going to go all the way out to x. And that's just going to go out as far as my graph screen allows it to. And you have to have the x in the top in order for it to graph the function. And then I'm going to go 2x dx. Okay. And so this is like us generating the table of values and then seeing what that pattern looks like on the graph and then being able to pick out the function. So I'm going to go ahead and graph that. And as you can see, it gives me that quadratic. And that happened pretty fast because I have a CE and because the integral was not too complicated. We'll try to do this one that way, and you'll see it'll take much longer. So that's another way to use the Math 9 capabilities in the grapher. Now the advantage to this is it creates a table. And if I go into table set, let's just go ahead and set this back at 0 and a delta of 1 so that I can look at between 2 and 7. Then when I look at my table here, I can see 2 is 4, 7 is 49. I can subtract those 2 to get my 45. So I can figure it out graphically that way, which is kind of nice. And then the next way to do this, and this is kind of interesting. So let's get rid of this. Let's clear this out because we don't have to put the integration capabilities in there. Okay, what we can do is we can actually graph the integrand like we would do this by hand. We can actually graph 2x. So there's 2x. And I'm going to actually zoom standard here. No, I'm not going to zoom standard. Let me set the window at -5 to 5. And let's see, at 2x, I'll go to minus, -6, -10 to 10. There we go. There we go. It gives you a little bit more of the graph. Okay, so 1, 2, 3, 4, 5. Oh, actually, I got to go out to 7, don't I? To see the whole shape if I were to shade this in. So let me redo the window. -10 to 10. Okay. There we go. So we can actually shade in from 2 to 7. And if I go out to 7, I'm going to be up at 14. So now, wow, I'm really not good this morning at doing my window. Let's go from -20 to 20. All I need really is the first quadrant, but okay. So we actually have the capability of shading this in just like we've been doing earlier in the unit. And the way you do that is you go second, calc, and you can actually calculate an integral, just like you can calculate a derivative. So I'm going to do a second calc 7. My lower limit's going to be 2, and I'm going to hit enter. And my upper limit, so it sets up my lower limit, the upper limit is going to be 7, and I'm going to hit enter, and it literally will shade in that and tell me it's 45. So that would be the third way of using your integration capabilities of your calculator to get answers. without really having to do the integration by hand like we did here. Okay, so pretty cool. And we're gonna try it on this, which is far more complicated, and you wouldn't be able to integrate this. So we have f of x is that rational expression, and it's increasing, and we know that this function is increasing on 1 to 7. Okay, what is the definite integral from 1 to 7? We want to know what the value is. Okay, so, and then it talks about an LRAM. We'll talk about that in a second. Okay, so I'm going to clear out this, which is going to clear out my graph. And I am going to go ahead and graph this so that I can work with my integration capabilities like we were just doing. So I have a numerator. I'm going to need to put that in brackets. So that's x squared plus 1. And now I can divide by that entire denominator. So I'm going to put that in brackets too. And that's the square root of x, move over to get out from under the radical, plus x plus 5. I put it in right as I see it. I put brackets top and bottom so that this is grouped and this is grouped like it's supposed to be. And then this is what I do. I look at this and I say, I need to go from 1 to 7. Okay, so I am going to set up my window from 1 to 7. I don't need all these negative x values. So I'm going to go from 0 to 8, just so that I have a little on either side. And I'm going to stick this back to minus 10 and 10, because typically they try to keep you in that standard window. And let's take a look at this graph. There we go. Okay, so that's actually from 0 to 8. I want to go from 1 to 7 and find the area of this region. So I'm going to go ahead and do a second calc. And a second calc integration. My lower limit is going to be 1. My upper limit is going to be 7. And there is the area from 1 to 7. It is 9.855. So then we know that is the area, 9.855. Okay, so so those are some of the capabilities of the graphing calculator with integration. Let's talk about graphing this in math with the graphing capabilities here. I'm going to keep this up here. So let's do what I'm saying is let's try to do a math 9 here. Okay, so from 1 to 7, let's go from 0 to 8 again, just to, because we're matching the window then, from 0 to 8, and I want to integrate this. So I want to see the antiderivative. So I don't have to type this whole thing in. This is kind of cool. I can use something called the vars key. And I go vars, and then I arrow to the right. I go right vars and function. So I'm going to hit enter, and I'm going to grab y1, and it just sticks y1 right in there. It's like a substitution key, and then x. So let's graph that. So it's going to be blue, and as you can see, it's going to take a while. And my calculator is thinking and thinking and thinking and thinking. And so this is why I don't recommend you do this on your calculator with anything that is rational and looks this complicated, because it takes literally forever to graph it, because it is graphing it point by point by point, and it gets really bogged down. So I don't recommend it. Mine's still thinking. I'm going to come back to my my PowerPoint presentation. We can watch this. I would be surprised if it finishes up before we finish this video. Okay, so I guess I'm going to have to stop it because we want to talk about this. So here is a g of x. It's the integral from -1 to x of this. And it says at what value does g of x attain a relative maximum? So the idea here is we don't even want to try to do what we're doing with this. We don't want to use our math. Oh, I think it even errored out. It didn't give me anything. Let's see what happened in the table. Oh, the table, it did give us something but as you can see, it took a really long time to do, and it's actually off the table. So let me, let's do like 40. Let's see if we can see it there. Yeah, see, look how slowly it graphs. So we don't want to bog down the calculator all day doing that. So we're not going to bog down the calculator by putting this. Let's see if we can get it to error out here. There we go. We're not going to bog down the calculator by putting this up in the y equals like we did here. So let me delete that, show you a different way of doing that. So I'm going to delete both of these now. We're going to talk about this question particularly. I don't want to put this into the grapher and try to find a maximum. So I know this is the derivative. I'm going to graph this. And remember, maximums is where the derivative goes from positive to negative. And I'm going to go in this domain. So let me set that up. So we are going to graph negative 0.5 plus cosine x cubed plus 2x close my parentheses. So that is the derivative. We know when the derivative goes from positive to negative that we've reached the relative maximum. I want to set my window for 0 to pi over 2. So 0 to pi over 2. And I'm not going to overshoot that window. I'm going to set it exactly 0 to pi over 2 because I just want to focus on where it's crossing the x-axis. And I don't want to get distracted by anything else. And cosine, you know, fluctuates between -1 and 1. So I'm going to go from -2 to 2. I think that's pretty safe. Whoops. The 2. There we go. Okay. So the other thing is, want to make sure you're in Radian mode. And so I've got it all graphed. I'm just checking this again. That looks good. -0.5 plus cosine. Okay, we can graph this. Okay, so graphing this looks like this. Okay, so this is the derivative. Notice that was much faster than trying to integrate it into the grapher. And then we know we go from positive to negative here. So this must be our relative maximum. We go from negative to positive here. This must be our relative min. So our relative max is about right here. And if we look at this tick mark, this must be 1. And this is pi over 2. Pi over 2 is about what? 1.5. So this looks like it's about 0.5. So this is the answer to this has got to be oops, the answer to this has got to be A. Okay, so we did the quicker way. Okay, we're going to look at this as fundamental theorem of calculus part 2, right? We're going to differentiate this and just look at this function here. Look at g prime of x and look for where it crosses. So the answer to this is A. I think I forgot to circle it though. Notice though the teaser, right? The minimum is right here, and that looks to be maybe 1.3, 1.4. I bet it's one of these two numbers. So we have a good teaser here if you accidentally give me the minimum. So, but this answer is A. Go ahead and circle A in your notes. Okay, so the essentials for anti-differentiation techniques. We need to know all the derivative rules and their anti-derivative counterparts. We've been stressing that in our flipbook all unit. That includes the sum and constant rules. Our use substitution, got to be really strong in that. Long division, completing the square. Those are good to know. But there's only 1 or 2 questions per test on that. And then look for patterns that you can apply to similar techniques. When we get back into the classroom, then we'll get the opportunity to kind of practice all of our techniques and distinguish between what technique is necessary.